Have you ever stopped to think about what's really going on chemically when you start your car or when you charge your phone? The answer is a fascinating type of chemical reaction called a redox reaction. And today, we're going to pull back the curtain and see exactly what they are and how they work. You'll see they are literally happening all around us, from
the powerful combustion of fuel that gets your car's engine roaring to life, releasing a huge amount of energy to get you from A to B,
to the clever little electrochemical dance happening inside the battery that's keeping your phone going right this very second. And yup, even that slow, quiet process of a bicycle chain getting rusty after being left out in the rain. All of these, from the fast and furious to the slow and steady, are driven by the exact same fundamental process.
So what's the secret? Here's our game plan for this explainer. First, we'll see just how common these reactions are. Then, we'll dive into the heart of it all, a beautiful dance of transferring electrons. We'll learn the chemist's secret bookkeeping trick using something called oxidation numbers, and then we'll use that new skill to balance a pretty tricky redox equation. And finally, we'll wrap it all up by sorting these reactions into 4 main types. Ready? Let's jump in.
So first up, just how widespread are these things? Well, we already know they power our gadgets and cause rust, but that's just scratching the surface. They're absolutely essential for making metals, for so many industrial processes, and even for the very biological reactions that keep us alive, like how our bodies convert food into energy. This quote really hits the nail on the head. You can't have one without the other. Think of oxidation and reduction like 2 sides of the same coin. As the saying goes, where there is oxidation, there is always reduction. They're a chemical package deal. So what's actually happening at the atomic level? Well, it all boils down to an elegant little chemical dance that's all about one thing, the transfer of electrons. Let's break down the 2 key moves in this dance. The first move is called oxidation, and the modern definition is beautifully simple. Oxidation is the loss of electrons. That's it. A super easy way to remember this is the little acronym OIL, for oxidation is loss. And of course, every dance needs a partner. That partner is reduction. So if oxidation is losing electrons, reduction is, you guessed it, gaining electrons. And the acronym for this one is RIG, for reduction is gain. So put it all together and you get oil rig. And this is the most important part. These 2 things are totally inseparable. When one atom or molecule loses electrons, gets oxidized, another one has to be there to gain those exact same electrons. It gets reduced. They happen at the exact same time, every time. Let's look at a classic example, making good old table salt. We can actually split the reaction into 2 half reactions to see what's happening. First, the sodium atoms each lose an electron. That's our oxidation. So where do those electrons go? Well, they're immediately grabbed by the chlorine molecule, which gets reduced. See how that works? The 2 electrons lost in the first step are the very same 2 gained in the second. The books are perfectly balanced. Okay, so tracking electrons in that simple reaction is pretty straightforward, but what about in really big, complex molecules? For that, chemists came up with a brilliant bookkeeping tool called oxidation numbers. So what is an oxidation number, really? Think of it like a pretend charge that we assign to an atom in a molecule. It's the charge it would have if we imagined all its chemical bonds were 100% ionic. It's not a real charge, but it is an incredibly powerful tool for keeping track of where all the electrons are moving. And to assign these numbers, we just have to follow a handful of simple rules. Any atom in its pure elemental form, its number is 0. An ion all by itself, the number is just its charge. The 2 big ones to remember are that oxygen is almost always a -2, and hydrogen is usually a +1. And here's the golden rule. In a neutral compound, all the oxidation numbers have to add up to 0. If it's an ion, they have to add up to that ion's charge. That's the key. Okay, so why did we learn all that? Because oxidation numbers are our secret weapon for balancing complex redox reactions, which can otherwise be a real headache. So let's roll up our sleeves and put this tool to work, step by step. All right, here's our challenge. We have to balance this beast of an ionic equation. It looks a little intimidating at first glance, but don't worry, we've got a system. We're going to use the oxidation number method. It's a 5-step plan. First, we assign our numbers to see who's gaining and who's losing electrons. Then, we make sure the electrons lost perfectly equal the electrons gained. And finally, we just clean up the rest of the atoms and charges. Let's do this. Okay, step 2, let's assign those numbers. Let's start with the dichromate ion on the left. We know each oxygen is a -2.
and there are 7 of them, so that's negative 14 total. The whole ion has a negative 2 charge, so the 2 chromium atoms must add up to plus 12, which means each chromium is plus 6. Once we follow that logic for everything else, we see it clear as day. Chromium goes from plus 6 down to plus 3. It's reduced, and sulfur goes from plus 4 up to plus 6. It's oxidized.
Now for the magic step. We have to equalize the change. Each chromium atom's number went down by 3. But wait, there are 2 chromium atoms in that ion, right? So that's a total decrease of 6. Now look at the sulfur. Each sulfur atom's number went up by 2. To make that total increase match the total decrease of 6, what do we need to do? We need 3 sulfurs, because 3 times 2 is 6. So we just put a coefficient of 3 in front of our sulfur ion.
We're so close. Next up, we balance the overall electrical charge. Let's do the math. On the left side, we have 1 ion at -2 and 3 ions at -2 each, for a grand total of -8. On the right, we have 2 ions at +3 and 3 ions at -2, for a total of 0. To get the left side from -8 to 0, we need to add 8 positive charges. And since we're in an acidic solution, we can use H+ ions. Let's add 8 of them. Perfect. Now both sides have a total charge of 0.
And for the grand finale, we just balance the atoms. We added 8 hydrogens on the left, so we need 8 on the right. We can do that by adding 4 water molecules. Now the final check, let's count the oxygen atoms. We have 23 on the left and 23 on the right. It's perfectly balanced. See? When you follow the steps, it just works.
Whew. Okay, now that we're masters of balancing, let's zoom back out and look at the big picture. It turns out we can group most redox reactions into one of 4 main categories.
We can usually sort these reactions into 4 types. Combination is exactly what it sounds like. 2 things combine to make one. Decomposition is just the reverse. One compound breaks apart into simpler pieces. Displacement is where a more reactive element comes along and kicks a less reactive one out of its compound. And finally, there's the really cool one, disproportionation. This is a special case where the very same element manages to be both oxidized and reduced in the same reaction. Wild, right?
So there you have it. We've seen how these fundamental reactions work, from the simple swap of an electron to the beautiful logic of balancing complex equations. This is the chemistry that's powering our batteries, our fuel cells, and our green energy future. So I'll leave you with this question. Now that you understand the engine behind it all, what other global challenges do you think we could solve with redox chemistry? Thanks for watching.